Welcome, everybody. Thank you very much for tuning in to this presentation where I'll be introducing the new SCIEX Triple Quadrupole 6500 LC-MS system, a new tool for achieving the next level of performance for steroid research. So first, let me introduce myself. My name is Michael Jarvis. I'm the Technical Marketing Manager for Clinical Research at SCIEX, and I'll be starting off with a hardware overview of the new components of the SCIEX Triple Quadrupole 6500 system featuring ion drive technology. Then I'll hand off to Dan Holmes, who is the Clinical Associate Professor of Pathology and Laboratory Medicine at the University of British Columbia and the Division Head of Clinical Chemistry at St. Paul's Hospital in Vancouver, Canada, who will talk about the analysis of aldosterone by LC-MS. The new SCIEX 6500 series is the newest introduction to the family of modern SCIEX instrumentation and joins the 4500 and 5500 systems. Like the 4500 and 5500 systems, it shares a compact footprint with dimensions of 32 by 32 by 24 inches. And it comes equipped with convenient integrated features such as the 6-position diverter valve and the syringe pump. Major advantages in LC-MS performance on this system are powered by ion drive technology, which consists of 3 principal components: the ion drive Turbo V source, the ion drive Q-Jet ion guide, and the ion drive HE detector. Furthermore, advanced dual RF electronics makes this system a no-compromise triple quadrupole mass spectrometer with capability to operate in 2 different modes, either high sensitivity mode with a mass range from 5 to 1250 Daltons, or extended mass range mode with mass range from 5 to 2000 Daltons. This system is also compatible with Selexion ion mobility technology for enhanced selectivity. So this system was designed with the philosophy of creating more ions, capturing more ions, and detecting more ions. The system-wide improvements include modifications in the Turbo V ion source, the Q-Jet ion guide, and the detector. All of these improvements serve to drive LC-MS performance to the next level. Let me start by describing the ion drive Turbo V source, designed with the idea of creating more ions. The larger diameter heaters are 11 millimeters in diameter as opposed to 4 millimeters on the original Turbo V source. The optimized geometry ensures more efficient heat transfer, which effectively desolvates and ionizes analyte ions more efficiently. These heaters cover a larger cross-section of the spray zone, resulting in a much wider sweet spot for optimization of probe position. Furthermore, these changes to the source design ensure more robust performance against fluctuations in gas flow dynamics and source-to-source differences. As we can see on this slide, this figure highlights the differences between the original Turbo V source and the new ion drive Turbo V source. As we can see, the much larger heaters provide much larger sweet spot for ionization and much more efficient probe optimization. The second component of the multi-component ion drive technology is the new ion drive Q-Jet ion guide, designed to capture more ions. This RF ion guide is a 2-stage ion guide. The first stage serves to better capture ions from the larger orifice. The second stage serves to better transfer ions to the Q0 region. This design provides high robustness and a better barrier against neutrals and microdroplets entering the mass spec system. Compared to the original Q-Jet ion guide on previous systems, the new ion drive Q-Jet ion guide provides ion transmission efficiencies which are 2 times better. In this slide, we can see a computed gas flow model showing flow through the ion guide. The larger diameter of the first stage ensures better ion capture, while the smaller diameter of the second stage ensures better ion focusing into Q0. The end result, more ions transmitted and fewer neutrals reaching Q0. The third and final component of the ion drive technology is the ion drive high energy detector, designed with the idea of detecting more ions. This detector ensures that sensitivity gains are not at the expense of dynamic range. Ultra-fast pulse counting allows 10 to the 8 counts per second, and this is a 20 times improvement compared to conventional detectors in previous mass spectrometry systems. The higher saturation point, combined with the pulse counting to ensure a low-end sensitivity is not compromised, results in a total dynamic range of 6 orders of magnitude. On this slide, we get a sense of the sensitivity gains on the triple quad 6500 system relative to the triple quadruple 5500 system. On the left side, we see a compound, verapamil, with a 6-fold gain in signal and a 4-fold gain in signal-to-noise. On the right side, we see a compound, ginsenoside, RB2, with a gain of 20 times in signal and a gain of 4 times in signal-to-noise. Overall, we expect that the average gain in sensitivity on the new triple quadruple 6500 system will be up to 10 times. As I've already mentioned, it's expected that the new HE detector provides an extended linear dynamic range of up to 6 orders of magnitude. As we can see here, we have a calibration curve ranging from 1 picogram to 1 microgram per mil of aldosterone. The inset in the bottom right-hand corner demonstrates that even at low concentrations, the accuracy and linearity of the calibration curve is very good. So in conclusion, the ion drive technology on the new SCIEX triple quadruple 6500 system drives LC-MS performance to the next level. It does so by improving analyte ionization and desolvation with the new ion drive turbo V source. It also improves ion capture with the new dual-stage ion drive Q-jet ion guide. And finally, the new ion drive HE detector improves sensitivity and extends the dynamic range. The overall performance of this system provides up to 10x more sensitivity compared to the 5500 series, and up to 6 orders of linear dynamic range. Furthermore, this system is compatible with the Selexion ion mobility technology, thus providing enhanced selectivity capabilities for challenging assays. And finally, this no-compromise system employs advanced dual RF electronics to allow for operation in 2 different modes, for either highest sensitivity analysis or for extended mass range analysis up to M/Z 2000. So I'd now like to turn over to Dr. Daniel T. Holmes from British Columbia in Canada, who will be speaking about the analysis of aldosterone by LC-MS.
Thanks, Michael, for that very interesting presentation about the 6500. Those look like really positive improvements. We're going to talk about some initial work that we've done on a difficult analyte on the 6500, but we'll start with our background of what we've done on the 5000. So we'll start with an outline. First, we'll talk about the research motivation behind a desire to measure aldosterone, looking at the structures, the sample prep, the chromatographic challenges that we had, and we'll be comparing the sensitivity of aldosterone determination on the API 5000 to the new triple quad 6500 system. We're going to talk about our research motivation behind measuring aldosterone. Aldosterone and related mineralocorticoids are of interest for those who are doing research in secondary forms of hypertension. And when we say secondary forms of hypertension, we mean curable forms that have a definite cause. Most hypertension doesn't have a well-defined treatable cause. Primary aldosteronism is the most common form of secondary hypertension and is thought to comprise up to 10% of hypertension in all comers. There's also increasing interest in the physiological effects of aldosterone and other mineralocorticoids outside the classical renin-angiotensin-aldosterone system paradigm. That is, we might call those pleiotropic effects. In other words, what effects does aldosterone have other than the effect of retaining sodium and wasting potassium at the level of the renal tubule, and therefore maintaining blood pressure? There's also an interest in measuring aldosterone in tissue. I've provided a couple of references here from a colleague, Carlos Gomez-Sanchez, and another researcher, Kieran Soma, from the University of British Columbia. This is a diagram of the renin-angiotensin-aldosterone system, and just as an overview, starting on the left, looking at the liver makes a protein, a globular protein called angiotensinogen, which is released into the plasma. And under the action of an enzyme produced by the juxtaglomerular apparatus of the kidney, the enzyme is renin, a decapeptide called angiotensin-1 is cleaved off. Angiotensin-1 is not physiologically active as far as anyone knows, but as it passes through the endothelium of the lung and the renal endothelium, it is subsequently cleaved to another peptide called angiotensin-2, which has a number of direct physiological activities. Relevant to us, angiotensin-2 has action at the adrenal gland to increase the production of aldosterone. Aldosterone, as I alluded to earlier, at the level of the renal tubule causes the retention of sodium and in exchange for potassium. And with sodium comes the water that surrounds that ion, and that maintains the plasma blood pressure by increasing the plasma volume. The concentration of aldosterone is very low in the plasma. It's in the picomolar range, and that makes it a difficult steroid to analyze, unlike cortisol, which is about 1,000-fold higher in concentration, measured in the nanomole per liter range. Why would we want to measure aldosterone by LC-tandem-MS? Well, it's a well-known problem that there are significant method-dependent biases in aldosterone rate immunoassays. And so when you're doing research and you happen to change vendors for your assay, you're going to see a big shift in the numbers. And we've seen that in our own research work. We've been through 2 incarnations of rate immunoassay, and we've moved on to LC-tandem-MS, and we have to adjust all of the methods and normalize them to one method in order to do statistical analysis. So LC-MS offers us a way of standardizing to something that's going to be more predictable and not have interferences from aldosterone-related compounds. The problem with RAAs really became significant when there was no longer an extraction step. They were the so-called homogeneous RAAs, and those are the ones that are used typically today. This has been a well-known problem that the homogeneous RAAs have some cross-reactivity with non-aldosterone steroids, probably metabolites of aldosterone, which is a particular problem in people with chronic kidney disease because the metabolite half-life is much longer. This is an example from Pizzolo et al. In Clinical Chemistry 2006, comparing different rate immunoassays with a chemiluminescent assay. And you can see from this comparison that the 2 RAAs compare quite well, but with the chemiluminescent assay, there's a large bias seen. I personally have tried 2 different RAAs in my own laboratory, and the slope between the 2 of them was about 0.65. Here's another slide from Scherpenbach et al. In 2006. And what this is showing is a mean aldosterone concentration measured with error bars by 4 different methods: Adaltis, Nichols, DSL, and an in-house rate immunoassay for aldosterone. And you can see at the time 0 point, for the same sample, the mean aldosterone concentration can be as much as 2-fold different. So when you have biases like that and you're trying to adhere to clinical practice guidelines, or you're trying to do meaningful comparisons between study specimens at different sites, you have a significant problem with normalization of your results. What are our available methods for aldosterone by LC-tandem-MS? Well, there's a method from Taylor's on the water symbiosis system involving a protein precipitation and analysis in electrospray negative mode on the Quattro Premier. There's also a well-known publication from Dr. Solden requiring online SPE and use of atmospheric pressure photoionization on the SCIEX API 5000. From Ursula Turpainen in Finland, there's a method for aldosterone determination on the SCIEX API 3000 using extraction with dichloromethane and diethyl ether and reconstitution with 50/50 methanol water. Finally, Quest Diagnostics reported an APCI method in positive ion mode in a book called Steroid Analysis by Macken and Gower. And finally, there's a derivatization method by Yashimata et al. What are our limitations? Many of the listeners will be from countries other than Canada and won't know some of the barriers we face in our public health care system. But we have very significant cost concerns in how we manage healthcare dollars here. So we didn't want the high disposables cost of solid phase extraction, whether online or offline. At the time of initiation of the method, we actually didn't have a vacuum system for a Hamilton Starlet, and so offline SPE that would be automated was not going to be a possibility. We did not have an APPI source and the extra pump needed for the toluene dopant. We wanted to have a liquid-liquid extraction approach because that's simple, but we didn't want to use dichloromethane and ether because of the cancer risks associated with DCM and the high vapor pressure of both solvents. So equipment was always a battle for us. We wanted to do this with the equipment we had, which was an out-of-the-box API 5000 system. So initially we tried methyl tert butyl ether in mixture with methanol in 9-to-1, but the presence of the methanol caused the columns to clog, and it was a fairly consistent pattern we were seeing of clogging columns every second run or so. So we moved to pure MTBE, 2,500 microliters, with 500 microliters of sample. Now that's a bit large sample, but trying to use 250, the LOQ was too high for our work. Using 500 microliters of sample, our LOD is about 20, and our LOQ, based on a 10-to-1 signal-to-noise ratio, is about 50 picomolar. We vortexed in a 5-millimeter Eppendorf bin and dried down in a 96-well format. We recon with 125 microliters of 2080 methanol water, which gives us much tighter peaks than 50/50 methanol water. All of our pipetting is automated, and the injection volume is 50 microliters into the LCMS system. In terms of IS and calibrators, we used D7 aldosterone from SCIEX, and we made weighed-in calibrators using aldosterone from Sigma, spiked into steroid-free serum from Golden West Biologicals. For reference, here are our mass spectrometric parameters, so the viewer can copy those down if they want to try this. And here's our solvent gradient. A is basically water with some ammonium acetate, and B is essentially methanol with ammonium and acetate. We're using a Gemini NX 3-micron C18 column that is 10 centimeters long, and we're using a C18 guard pack to go with that. HPLC is a Shimadzu system. Here, a typical chromatogram from a real patient sample. This patient is about 334 picomolar, which is smack in the middle of the normal range. And you can see that there are a number of interfering shoulders that are chromatographically separated. That shoulder we've determined is probably 18-hydroxycorticosterone. That's what it's looking like when we do spiking experiments. But the chromatography is quite good, even below the limit of quantitation. This is 31 picomolar, and you can see we have a decent peak there. You can see more clearly the interfering chromatographically separated peaks. We have good linearity up to 3,500 picomolar, and we have good precision between 3 and 5% in the main portion of the analytical range, and somewhere around 10% down at the limit of quantitation. In terms of recovery, we did direct mixing experiments with high pools and low pools and got good recoveries. We've done extensive interference studies in coordination with SCIEX, and we've only found that 18-hydroxycorticosterone has the potential to interfere. That's that shouldering peak. It would have to be very high in concentration in order to accomplish that, and we have never observed that in any samples that we've actually run. The qualifier and quantifier peaks compare very well, as do EDTA plasma versus serum. Naturally, we did a comparison with rate immunoassay, in this case the Siemens code count, and we got a slope of 1.15 with a correlation coefficient of 0.94. So there is a little bit of bias, both proportional and constant bias, not really surprising, and perhaps more scattered than people would expect. But there should be no concern. When we did a comparison versus LCMS at another site, using a different method, supported liquid extraction in this case, and their own LCMS method for aldosterone, also on an API 5000 system, we get a much tighter slope, and we get a coefficient of determination of 0.96. Why is more sensitivity desirable? Well, it'll improve your limits of quantitation. You can use lower sample volumes, and you can use smaller injections, and if you need to, you can do a re-injection. So there's a number of reasons why we would want to have better sensitivity when we're doing low-concentration steroids like this one. So we've done some initial investigation on the 6500 system in the determination of aldosterone. You can see on this slide that we can see the aldosterone peak spiked into steroid-free serum down to about 3 picomole. In terms of measurement in peripheral blood, that would handle just about any research interest that anyone could have. We have good linearity up to 1,000 picogram per ml, which is 2,800 picomole per liter, and a good correlation coefficient on the calibration curve. But this is what we're really interested in. at level of 40 picomole per liter, 39.6 picomole per liter, which is below our LOQ, you can see that we have about 500 counts per second on the 5000 system, but we have greater than 2000 counts per second on the 6500 system. So that's an improvement of about fourfold. So in conclusion, LCMS is an appropriate method of analysis for mineralocorticoid since it avoids all the problems associated with RIA. And in fact, we've done a number of other mineralocorticoids in addition to aldosterone, the most difficult of which, in terms of its concentration, would be 11-deoxycorticosterone. But we've also done some of the 18 steroids. We've developed a method of analysis for the 5000 system based on LLE with an LOQ of about 50 picomole per liter. The new SCIEX 6500 system should provide a sensitivity of about fourfold and perhaps an LOQ down to the 10 to 20 picomole per liter range. That would be in real specimens, not in spiked specimens. The extended linear and dynamic range is up to potentially 6 orders of magnitude, and that will afford analysis of very high concentration samples without the need for dilution, which can be a convenient thing. What context do you see very high concentration samples? Neonates, on occasion, we've seen up to 50 or 100,000 picomole per liter. Samples from the adrenal vein, where we've seen concentrations of up to around 300,000 or 400,000 picomole per liter, and of course urine samples, which are in the nanomole per liter range. So thank you for your attention. I'm going to hand the talk back over to Michael Jarvis to finish up.
Okay, well, I'd like to say, first of all, thank you very much to Dr. Holmes for a very interesting presentation on the analysis of mineralocorticoids. And thank you also to everybody who's listened into this presentation today. I hope that you found it very informative. And lastly, I just want to put up a slide showing the speaker contact information. If you have any questions about anything that you've heard here today, you can either go to the website at www.absciex.com, or you can get in touch with the authors of this presentation, either myself, michael.jarvis at absciex.com, or Dr. Holmes at dtholmes@mail.ubc.ca. Thank you very much.